All right, well, good morning and welcome. My name is Peter Bartlett. Welcome to the Simons Institute and the workshop and summer school on deep learning theory. I'm very happy to have you all here. We run, our typical thing is semester-long programs. We run 2 of those each semester. But we also run these shorter events, smaller events, I guess, in the summer. So this workshop and summer school is part of the Deep Learning Theory Summer Cluster. Big thank you to the NSF and the Simons Foundation for funding the collaboration behind this. Also, a big thank you to the organizers for the workshop and summer school, Nati Sribro, Spencer Frei, Surya Gunasika, Pritam Nakiran, and Yongtak Son. Thanks to those folks for putting together a great program. Looking forward to an exciting week. Before Nati says a few words about the workshop, let me say a little bit about various logistics things. So for masks, the university strongly recommends wearing masks indoors. For food and drinks, you should have discovered the snacks out the side there, and the coffee. We'll have those during breaks. Please don't bring them into the auditorium. Water is fine. For lunch, you're on your own. If you want to leave bags and things in the building, there are lockers on the far side that work with a PIN code. Omid Far, our videographer in the booth there, is going to be connecting speakers, computers, and microphones and so on. And also a big thank you to Elizabeth Yuen, who did all the local arrangements for this workshop. All right, well, looks like it's going to be a great week. Looking forward to the lineup. Nati.
Okay. Welcome, and thanks everybody for coming. Happy to have you here for the week. As Peter said, this workshop in summer school is part of an ongoing collaboration that involves both several weeks here in the Simons and other ongoing activities, including hosting a bunch of really excellent postdocs. And in fact, this workshop was organized by many of these postdocs. I'm here presenting, but really all the work, 99.9% of the work was done by our excellent postdoc Spencer, who's going to be speaking soon, Yongtak, who is there, and Pritum, who I haven't seen. Oh, there, everybody. Sorry, can't see people with a mask. And sorry, who'll be joining later, I hope. So we have a combination of tutorials, which will be a bit longer, and most of them stretch over multiple meetings, and research talks. The tutorial, we intentionally try to have a mix of mostly theory. I mean, this is a workshop about theory, but to stay kind of, and we think it's important to be, guided and informed by actual problems. We also have several tutorials really about how do these things look like when, not when we just prove theorems about them, when we actually want to try to use them. And I hope you'll enjoy those as well. We do hope it's going to be an active and engaging week with both good talks and questions and discussions. We do, of course, want to remind everybody to keep all these discussions both civil and also progress things, so keep in mind of the time that we have with great timing. We have also actually a working clock installed to help us keep track of time, and really to ensure that things really do stay kind of productive and on track. The chairs will take a more active role and act as also as moderators as necessary to kind of moderate the discussions. So with that, let's start. And our first tutorial is by Spencer Frei, who's a postdoc here in Berkeley with a collaboration after finishing his PhD in UCLA last year. Thanks, Spencer.
Thank you. Yes, so today we'll be starting in the tutorial with something about statistical learning theory, and in the second tutorial today we'll talk a bit more about optimization and how do neural networks and deep learning kind of fit into these. Okay, so we'll start by just kind of getting the setup ready. So we're going to be talking about supervised learning problems in this tutorial. So we assume that the outcomes y come from some set of possible outcomes calligraphic y. We have some features x that come from some feature space calligraphic x. We assume we have some data sets of pairs x's and y's. And our goal is to choose some function f that goes from x to y that is able to predict well on some other pairs x and y that we haven't seen before. And we can define good in many ways. We'll be using kind of a loss function that takes two different inputs from this label space y and outputs some real number. So kind of two canonical examples are for binary classification. You can have -1 and +1 labels, and you might be interested in the 0-1 loss. So the probability of misclassification error, or basically saying that if you're 0 if you're correct and 1 if you're incorrect. Or we could be looking at this regression problem, and we might be interested in something like the squared loss. And so we'll be making some assumptions about the problem. These probabilistic assumptions that we're going to have some distribution P over x and y, which we don't actually know, but we do have the ability to take samples from it. So we have some samples x1 y, of pairs xi yi from 1 to n, and then some test sample xy. And our goal is to be able to have small population risk for this test example, right? So the expected loss for this predictor f, if you have the actual label y that comes from the distribution, right? And so I kind of jumped the gun a bit before, but if we have a pattern classification task where we have binary labels, the expected risk from the 0-1 loss is this probability misclassification error, and you can derive analogs for like the squared loss or whatever loss function you want. Okay, so the key difficulty here, right, is that we don't know what this distribution P is. We only have samples. And so to try to translate what's going on from samples from a distribution to some fresh example from the same distribution, we have to use statistics. And so the kind of main paradigm that we'll be talking about is trying to look at what happens if you take these samples and minimize some risk on these samples and hope and try to characterize when we can hope that this test error on like a fresh test example that's independent from these samples, the training sample is xi to yi, the hope is that this is going to be small if this empirical risk is small. Right. And the trouble here is that if we take some estimator that's defined in terms of the samples, this is a random function, right? Because we have random samples from a distribution. Some function of those random variables is going to itself be random, right? So this empirical risk, or the population risk of this estimator, is going to itself be a random variable. Right? So because it's a random variable and we want to make it small, we could either hope for saying that its expected value is small, or that it's going to be small with high probability. And so the kind of key question that we want to ask is whether or not we can construct some estimator, f hat n, that is able to compete with the best possible risk achieved for this distribution. Right? So the best possible risk could be defined in terms of the minimum possible value achieved by the population risk over all measurable functions from x to y. Or more generally, this might be a very strong desire to get something like that. We can instead hope that we compete with the best risk for some reference function class, right? So we can say our hope is to compete with the best linear classifier or the best neural network. And this is something that we can kind of, this is a type of assumption that we can make that we hope corresponds well with whatever reality we think the actual problem involves. And so this is what we're going to be talking about, is trying to understand when we can hope that this excess risk between the estimator f hat n and the best possible risk achieved over some function class is small as a function of certain properties of this function class. Okay, and so if you just try to decompose, the first thing that you might try to show that this excess risk is small is to decompose it into two quantities. One that we can control, and one that's just in terms of having a good estimator, and one that's just a property of the function class itself with respect to whatever distribution we're looking at. Right. So the approximation error is the kind of is what we're losing by just looking at this function class as opposed to looking at all measurable functions, say. And that's what this f star is the minimum risk achieved over all measurable functions. And the estimation error is the gap between the population risk under our estimator and the best possible risk under this function class f. Right, and there's a clear trade-off between these two quantities, because if we have a larger function class, then we can approximate things better. But we will see in the remaining slides that this is going to involve a larger estimation error. And on the other hand, we also know that if we're going to have a larger sample size, we can control the estimation error, and this doesn't have any effect on the approximation error because the number of samples doesn't appear anywhere here. Yes, I think there's some text down there. I'm not sure if we could move it up a little bit, but we'll see. Okay, so we're going to, in the sequence, we're going to be focusing on trying to control this estimation error, right? Because this is something that we as statisticians can actually do something about. And our goal is to be able to characterize under what properties of f this thing is going to be small. All right, so if we consider, we're going to be focusing on one particular algorithm that constructs an estimator, which is empirical risk minimization, right? Which is something I mentioned before, where we're going to pick the function within this function class, calligraphic f, that minimizes the empirical risk, right? This is something that we possibly could do, right? We're going to ignore whether or not we can actually devise an algorithm that finds the empirical risk minimizer for now. In the second tutorial, we'll talk a bit more about how we can actually minimize this empirical risk for neural network problems. But let's just ignore this for now and assume that we're actually looking at the empirical risk minimizer. And we want to be able to say, when is this empirical risk going to be small, if that implies that the population risk for this empirical risk minimizer is also going to be small. All right, so, and I guess also just to note, if there are ever any questions, please feel free to interrupt me, raise your hand, say something, and happy to answer. Okay, so our goal then is to try to characterize when the excess risk between, this gap between the risk achieved by the empirical risk minimizer and the best function in the function class is small. So we're going to decompose this into a sum of 3 terms. Okay, so this first term here is the gap between the population risk of the empirical risk minimizer and the empirical risk of the empirical risk minimizer. The second term here is the gap between the empirical risk of the ERM and the empirical risk of that best function in the function class, which is measured over the population risk. And then this third term is the gap between the empirical risk of this best function in the function class and the population risk of the best function in the function class. Okay, so this term in the red, right? The empirical risk minimizer is something that minimizes the empirical risk. And so its empirical risk is going to be smaller than the empirical risk of any other function. So this term is going to be negative. This third term, right? So we have some fixed function in the function class that doesn't depend upon the samples at all. Right? So the average of this quantity is going to be the same, of the empirical quantity is going to be the population risk. Right? So there's no dependence going on here. So we can just take averages and this will be 0 in expectation. So if we take expectations on both sides of this, what we're left with is that this gap between population risk of ERM, best possible population risk from the function class, is bounded just in terms of this first quantity here. Right, and so our task then, in order to be able to control the estimation error, is just to be able to control the gap here, right? The gap between the population risk achieved by ERM and the empirical risk achieved by ERM. Okay, so this term is troublesome because the issue is that the ERM is a function of all the random variables x1 up to xn. Right, so because of that, we don't know that the ERM as the function of each sample is going to be the same in distribution, right? Because we could have the ERM could be doing something that depends very specifically on the samples themselves in a particular way. So it could choose to do something just for one sample because it's one sample. So we can't expect this to have the same distribution as some test example, right? Because it could have these odd dependencies on things that we've seen before. And so we could try to do something trivial or something perhaps naive, which is to bound this gap by just the maximum possible value that could be achieved by this gap over the whole function class, right? And if we can show that this quantity is small as a function of n, right? L hat depends on n. Then we could have a control over this quantity, which would give us control over the estimation error. Right, and this is kind of what we'll be talking about in the remainder of this tutorial, is trying to quantify what properties or characterize what properties of this function class f allow for this quantity to be small. Right, and as we mentioned before, more complex function class or a bigger function class will allow for better approximation error. But presumably there would be some trade-off going on here where this quantity might be larger if we have a huge function class f, right? Because that only gets larger as we increase the size of f. Okay, and so that's what we'll be talking about in the remainder. And just some notation for what we'll be talking about in what follows. We'll be looking at a function class, and the standard setup that we've been looking at is some loss applied to some function f, which comes from a function class. So we're going to be looking to this this composition class of functions that are f composed with L, and we'll look at z's that are just the pairs of x's and y's. Okay, so just to reframe what we were saying before in terms of L's and x's and y's, in terms of g's and z's, right? We're going to be looking at a class of functions that say have bounded output, so it's from 0 to 1. We have IID samples z1 to zn, and then we have some test example z that is also identically distributed and independent. And we want to be looking at this uniform quantity, which is the maximum possible value achieved over the function class of the gap between the population risk under G and the empirical risk under G. Right, and so we can write this as the supremum of this operator P, which just takes expectations with respect to samples from the distribution, or for the test sample. Pn is the measure that's the empirical measure over the training data. And in the remainder, we'll just be using this notation to refer to this quantity U, which is a norm over the function class. Right, and what we'll say is that if this quantity U, this norm, if it tends to 0, this is called a uniform law of large numbers. And if we have such a thing, then we're in good shape to be able to control this gap between population risk and empirical risk for the ERM. Just rewriting everything that we've already talked about. We do this trivial upper bound of saying that this gap is going to be at most the largest gap over the whole function class. Reuse the definition of G to put it in, the L of F to put it into G form. And this is just this U norm bound. Right? Yeah.
Sorry, what's Z?
Z is pairs of X and Y. Right. So now our task is then to understand when this uniform law of large numbers holds. Right, and some properties of this function class G should determine that. Okay, and we'll call this function class G a Glivenko-Cantelli class if for this distribution P, if this uniform law of large numbers holds for this class. Right, and just to remind people of the setup, P is the distribution over Z, Z1 to Zn are IID, Pn is the empirical distribution. And G is some set of measurable functions that have, are to 0, 1 and have finite expectation. And Pn minus P we can think of as an empirical process. So it's a stochastic process where we have indexed this stochastic process by the function class G. And this norm is given by the maximum possible value of this function of this process. All right.
And function class being data dependent.
In this setting, we're not allowing that, but the ERM could depend on the data. Okay, so first question we might ask is, are all function classes Glivenko-Cantelli? This is not the case. So for instance, we can consider this function class that is given by indicator functions of finite subsets of R. Right, so it's going to be equal to 1 if Z is inside this set. It's equal to 0 if Z is not in that set. Right, and so for a continuous distribution, because the measure of a finite set is 0, PG is going to be equal to 0 for any function from this function class. But the supremum over this function class is going to be equal to 1 for all n. So does anyone have, can anyone say why this is the case? Why is it that for any fixed G, this is equal to 0, but the supremum over the empirical risk of the empirical measure is equal to 1? So if we want to show that, we need to construct some set S such that that we're going to have that the empirical measure is going to be equal to 1, and we want a finite set such that we can guarantee that G is going to be, this average of G is going to be equal to 1. Any ideas? Right, so we could just take this set. Let's see. We could just take this set S to be equal to Z1 up to Zn. Right, and then it's the case that indicator that Zi is an S is equal to 1 for all I. Right, cardinality of S is finite. Right, so 1 over n, sum from 1 to n, G of Zi is equal to 1. Right, so the thing that goes wrong here is that this function class is so large that we can capture anything that's going on with each sample that we observe in a very not uniform way. Like we can just choose to do something individually for each example because this function class is so large. Right, and this is really the problem for being able to have uniform convergence is that when the function class is too large, you can come up with these examples where you can do very sample specific things that will not be able to generalize well to test examples. And so that's really what we're going to be talking about is trying to formalize how it is that a function class can be too large, and what is it that makes this class large, and what quantities can we use to characterize that. Okay. So next I'll talk about VC dimension. And so to start, we'll need to define this growth function. So I guess I'm going back to using f now, but let's consider a class of functions f that is going from x to binary output, like 0, 1, minus 1, 1, also the same. And consider a set of examples x1 to xn. And we'll use this notation f of x1 to n, which is going to be the set of all possible n outputs that can be taken when you're taking a function from the function class and applying it to each possible sample from this x1 to xn. So this is a subset of 0, 1 to the n, right? This is a vector of n values. F is going to this binary output. And so it's going to be a subset of vectors, of n-dimensional vectors that take values 0 and 1. And the growth function is going to be the maximum possible size that this set can be when you take n examples from x. Okay, and the key thing that is useful about this growth function definition that I won't go into much more detail about is that we can bound this uniform, this expectation of this u, this norm between p minus pn empirical process, by something that's at most logarithmic in this growth function. Okay. So if we can characterize what properties of the function class allow for us to have a small growth function, then this will be able to say that we have a uniform law of large numbers, which allows for us to say that population risk and empirical risk will be close to each other. Right. So what are some? Oh, yeah.
What's x1 over there on the left-hand side?
Here. This one? Yeah, so this is just notation to denote, instead of saying x1, comma, dot, 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 comma, xn, it's just notation to say like the set of all possible outputs. So,
This has nothing to do with x1 to xn over there, or are you just like representing that?
yeah, so it's saying, so this notation means that we're going to have a sequence x1 up to xn, and that we're looking at all possible n-dimensional vectors that where the ith coordinate is f of xi. Okay, so I was saying if we can show that this growth function is small, like, then we're in good shape to be able to establish this uniform law of large numbers. And some trivial upper bounds that we could start with, right? This set is indexed over a function class f, right? So it has to have cardinality at most f, the size of this function class f. We also know that this function class is a subset of 0, 1 to the n. So we also have the upper bound of 2 to the n. And you can think about what happens if this is actually equal to 2 to the n, right? So if this is equal to 2 to the n, this means every possible labeling of these n xi's, right? So if we take a vector of n and we look at, we can either take 0 or 1 for each one, 2 to the n such vectors. If this growth function is actually equal to 2 to the n, that means that for every possible labeling of those n numbers, there is some function in the function class that can exactly label those. Right? So if you can think about this as having some possible random labels for some sample of n samples, and there's always some function in the function class that can exactly label those n labels, then the growth function will be 2 to the n. Right, and the thing to note is, if we have this growth function as 2 to the n, log of 2 to the n is n, and so we get something that's completely useless, right? This is not going to say that the estimation error is going to decrease when n tends to infinity, but this upper bound doesn't tell us anything at all. And so we can define this quantity, the VC dimension, the Vapnik-Chernovenkis dimension, in terms of this growth function. Right, so we'll use this definition that this function class shatters a set of D examples if the cardinality of this set that I was just mentioning, the number of possible labelings of these D examples is exactly equal to 2 to the D. Right, and the VC dimension is the largest such D that is possible. Right, so that's what this quantity is saying here, is that the maximum over all possible integers D, such that this growth function applied to these D examples is going to be 2 to the D. And the kind of fundamental theorem of statistical learning theory is that when you have samples that are bigger than this VC dimension, that the expectation of this stochastic process, the norm of the stochastic process, is going to be bounded by something that it's growing like root D over n. Right? D is the VC dimension. So as long as you can guarantee that the number of samples is bigger than the VC dimension, we can have this uniform law of large numbers and be able to say that the estimation error is going to be going to 0. Sorry?
What's the base of the log?
I'm not sure what the tightest one is, like their exact contents, but they're all equal up to constants. So you can take log 2, log e. Yeah, since there's an O there, it's not that big of a difference. All right. Okay, so now we've reduced our problem to
One more question. So here you're assuming that each x1, x2 are independent in some ways.
So there's nothing here that has to do with independence. This is just the kind of a set of examples.
So what I mean is like if f of x1, f of x2 is dependent on f of x1, then your shattering dimension might be, even though it might be less than d. Is it true?
So these are all just combinatorial quantities, right? We're just saying if you have d examples from this set of inputs x, does there exist some function, like any function from this function class? So it depends how you define the function class, I guess. But like if you think about linear classifiers or a neural network, you could maybe consider more contrived ones. But I think these are all combinatorial quantities that don't involve anything about statistics or dependence.
To achieve the second bound, do you not need IID assumption on the exercise samples?
To achieve, sorry?
To get the VC theorem, you do need IID assumption on exercise.
Yes, so this is the definition of the VC dimension does not involve statistics, right? So it's the theorem is the thing that connects this using independent samples that actually involves these combinatorial quantities. Right. So now in order to show uniform laws of large numbers, it suffices to be able to characterize what is the VC dimension of these function classes. And so next I'll describe what is the VC dimension of ReLU networks. So we'll consider this class of -1 and 1 valued functions that are computed by a ReLU network with L layers and P parameters. So parameters here is like the number of edges in the graph, and K hidden units with ReLU activations. Then this theorem by Bartlett, Harvey, Law, and Mehrabian is able to give upper and lower bounds for what the VC dimension of these ReLU networks are. So we have, which is of order PL, where in ignoring log factors that depend on K and L and P. And the thing to note is that this is able to give a guarantee for having, as long as you have a number of samples that's bigger than number of parameters times the depth, then we can guarantee that this empirical risk is going to be close to the population, right? Just by substituting in that VC dimension bound that we had before, right? We're going to have a root n, root PL over n, ignoring log factors, right? And so something that's a little unsatisfying about this is that the number of parameters in modern neural networks is very large, right? So if P is 1 billion and we only have 50,000 samples, then this is not a very useful upper bound. And so the hope is that we can do something better than this using some different tools. So that motivates this other complexity that we'll be talking about, which is Rademacher complexity. So to define Rademacher complexity, we take these epsilon i's, which are going to be uniform Rademacher random variables. So Rademachers are uniform plus minus 1. You can kind of think of these as random labels in a sense. So say if we have some examples z1 up to zn, we can think about measuring the kind of fit of a predictor G with these random labels by looking at the average of these epsilon i's times the G of zi. Okay, so you can think of if G is going to be outputting something that's exactly equal to epsilon I every time, you get epsilon I squared, and this quantity is going to be equal to 1. Right? And this is it's kind of like a correlation between the epsilons and the G is evaluated on the zi's. Right? And so if this predictor is able to fit random labels well, then this would be close to 1. And if not, then it might be something that decreases with n. Okay, and so we can use this to define the empirical Rademacher complexity of a function class, which is just the expectation over these Rademacher random variables of the largest possible value that can be achieved by a function class of this quantity that's the average of the epsilon i's and the G of zi's. Right? And so if for any possible epsilon I, right, any possible labeling of 1s and -1s, there is some G that exactly equals epsilon I, G of zi is equal to epsilon I for each I, then this is equal to 1, and we are not, this is a very large upper bound on what can be achieved. And we might hope that if there aren't G's that can do that, then this is a quantity that would be smaller. right? And so this is empirical because it's defined in terms of zi up to zn. And the actual Rademacher complexity is just going to be the expectation over these zi's that are taken for IID from the distribution. Any questions? All right. So why is this useful? Well, first we can bound this expectation of this norm, so this U quantity, which governs the uniform law of large numbers, by something that's a mostly constant factor times the Rademacher complexity, right? And in fact, if we're looking at just variables which are bounded between 0 and 1, we have a very tight characterization showing that this quantity is actually very tightly bounded to what's going on with the Rademacher complexity. So basically, the Rademacher complexity will tend to 0 if and only if this expectation of this norm, the uniform law of large numbers norm, goes to 0. Right. So this is quite nice. At least now we have this other quantity that can be able to give us this uniform law of large numbers. And so the question is whether or not this gives us something different than VC dimension. Like, what else can we do with this new characterization of the uniform law of large numbers? Okay, so the main reason why this is that I think is a much more useful quantity to actually use and for understanding statistical learning problems is because there is a calculus to Rademacher complexity. So for instance, if you have a set of functions that's a function class that's larger than your other function class, then the Rademacher complexity increases. If you take a scalar quantity that multiplies every single function in the function class, that scalar comes out. If you just add some possibly some other function that is bounded, then you only increase your Rademacher complexity by at most 1 over root n. And so this doesn't actually affect much of what's going on. Right? It's well behaved under convex hull, and one of the most useful facts is this contraction principle, which is that if you take compositions of different function classes, where with a single function, right? So we have some function L that is bounded in Lipschitz, then the function class that is defined in terms of that composition, right? So this kind of G that we were talking about, that it was defined in terms of L composed F, also only increases the Rademacher complexity by at most a constant factor plus something that vanishes as the number of samples goes to infinity. Right? And so as we were talking about before, we often want to look at losses composed with functions when we're trying to understand learning problems. And so this is an extremely useful fact for trying to characterize the Rademacher complexity of function classes and to get a handle on the sample complexity for a given problem. C is universal, yes. And so we can now think about what is the Rademacher complexity for ReLU networks, right? So in the same way before we were talking about the VC dimension for ReLU networks, maybe having a bound that only from Rademacher complexity could give us something that wasn't easily available in the VC dimension argument. And so we'll look at, let's say, a depth L ReLU network where sigma is the ReLU activation. And let's assume that we have, Frobenius norm bounded in each layer by B. Okay, so there are stronger results than what I'm showing you here, but this is a very clean and simple result to show. So if we have any training set of data where we have features X and then binary plus minus 1 labels, and the data are unit norm, the Rademacher complexity of this function class is something that grows with 2b to the L over root n. Right, so this exponential L dependence is maybe suboptimal, and there's a lot of work that tries to improve on this bound. But something that's very noticeable, even with this result here, is that the width of the network, or the total number of parameters in the network, does not play an explicit role. Right here, the only thing that appears is the depth and the bound on the norms of the weights. Right, so unlike in the VC dimension argument where we needed to have that the number of samples was growing with the number of parameters, this doesn't actually require that. Right? And then that's quite nice because if we're able to say that the norm of the weights found by gradient descent in a neural network is small, then it is actually amenable to being able to say something using classical tools of statistical learning theory.
Sorry. So how do we calculate this bound for a neural network?
Yeah, so next slide we'll go into proof sketch for how we might actually do that.
I mean, if we give a neural network, do we just train it and get to the norm of it?
Yeah, you can calculate. So if you train a neural network, you can calculate the norms of each layer, right? I mean, if it's not in this exact form, this is not going to give you anything. There are variants of Rademacher complexity bounds for different neural network architectures. I mean, the problem is, and I'll talk about this later, is that so this does give you some control over the gap between the empirical risk and the population risk of neural networks in some regimes, right? Where B is like smaller than a half, right? Then we have something, right? This is something that actually might be meaningful. But if B is larger than N, right, then this is not going to give us something meaningful. And that you can empirically look at whatever the norms are, and this may or may not be a useful bound depending upon what the norms are. But it just kind of depends upon how you're training. Are you early stopping? Are you using L2 regularization? These types of things could allow for this bound that we have on the weight norms to be smaller, which could allow for more applicable theory. But that might not be the optimal way to train the neural network, right? It could be the case that the best population risk achieved could be when the weights are really large.
I mean, if we train neural network, the B here, it depends on the training set, right?
Yes.
So that means your function class depends on the.
Yeah, so there are data-dependent versions of this Rademacher complexity bound that can get around this, or you can allow for that type of dependence. That what's presented here, it doesn't allow for that necessarily.
Sorry if you answered this in his question, but when you're kind of calculating the empirical Rademacher complexity, when you're training your neural network, why can't you just fix the weight norms to be a half?
You could.
Or is it just an optimization?
Yeah, it's an optimization question, right? The question is whether or not you could have small empirical risk and how do you actually constrain that? I mean, you could do some type of weight normalization, I guess. But yeah, I'm not sure what it actually results in terms of gaps between what is optimal or not, but you could do that.
Thanks.
If you had used VC dimension, then the complexity that you got was linear in L, but here you are getting a complexity that's exponential in L. What's the trade-off?
Yes, so this is not tight. This is a very simple bound that the proof can mostly be shown in one slide. There's a lot of work that goes into trying to make this better. Yeah.
The exponential balance in L is in B to the L is definitely right.
Is it?
Yeah, just because of scaling. So now that if you multiply, if you scale the weights with B, then since at every layer they got multiplied, the output gets scaled by B to the L. And so just the scale is B to the L. So since the Rademacher complexity is sensitive to scale, it doesn't necessarily scale as B to the L. And you can also
That scales the network, but that doesn't necessarily scale the correlations between epsilons.
But because it's homogeneous, I think that might be right. But then there's all the spectrum. I'm trying to think of the spectrally normalized bounds and how they, Matusa.
Yeah, you can embed a linear function in this network. So take a linear function, you just stack it, So you have there's a tight lower bound, which is like what Matthew was saying, but it's getting a linear function in network. But that said, I wouldn't exponent is bad. The P is the bound on the Frobenius number.
Yeah.
So you have to have that. You stop at every time.
Yeah, but you can do that, right? So you can just, as Matthew said, just take a. We know that for linear predictors and unbounded dimension, then sort of normal for square things like, and you can just take a linear predictor with some norm, and then take break it up into a product of a bunch of diagonal matrices. Each one of them would have norm, which is the L through. So yeah, so B to the L is definitely tight. It's true that you can get maybe complex control in terms of other parameters, but if you're only looking at the Frobenius norm, we don't know if the 2 to the L is tight, but the B to the L is tight. Yeah, but the basic, I mean, I don't remember who answered. The basic notion of why you need kind of the exponential dependence of L is because the scale of everything scales with as a product of the layers. So whenever you have kind of norm control, and we're only relying on norm control of each layer, you kind of expect to have some kind of exponential dependence in the product of the layers.
For sigmoid networks, this argument would not necessarily.
So yeah, this is for ReLUs. It's much easier to do the argument. For sigmoids, it's like more careful with it. Yep.
So what happens at b equals 1/2? Like, what if is there like a phase transition of some kind, like when b is less than 1/2, like where you now want a bunch of layers?
Yeah, well, I guess also because of the scaling, is if b is less than 1/2, right? The output is going to be very small. Right? The output is going to be exponentially small in L. Right, so you'll be able to guarantee that the population risk is going to be close to the empirical risk using far fewer samples, but that's because the output is going to be very close to 0 every time.
I see.
Right, because
I see.
Wait, is this plus minus 1 output though? I thought that you said the network was a classification.
yes, but so this F, right, is homogeneous, so the norms we could pull out. So we have, so maybe I guess I have a proof on it in the next slide, but the network itself is going to be something that's 1/2 to the L, let's say. Right, so yes, you're gonna have 1 times 1/2 to the L, or minus 1 times 1/2 to the L.
I think Anmal was asking about the VC bound too. Like that one had a P, right? So that P can be exponential in L. Is that the idea?
So, sorry, but P can be exponential.
There was like a bound for VC.
Yeah, so P there is going to be a sum. It's not going to necessarily be exponential unless you have a very weird network, right? So P is like P would be, say, sum of L of m sub L times m L minus 1.
Yeah.
So that's not necessarily going to be exponential in L.
Is it possible to restrict the lower bound of the norm?
The lower bound. I'm not sure. So the complexity of a function class where the norms are at least something.
Yeah, I mean, now the function class is norm is upper bounded by t, right? Also be lower bounded by something, and
so the norm of WI is going to be lower bounded by something.
yeah, restricted.
Yes, I suppose that's possible. I'm not sure what it would look like or what you would buy. Yeah, I think that's possible.
Yeah,
Then it will be not the upper bound but lower bound with complexity, because you say that the weights
so
pretty much will be trade.
So I think I'm just going to try to move on a little bit because there's a lot of other stuff that I wanted to get to, and maybe I'll skip over this proof. Yeah, I'll skip over this proof and just kind of start to conclude. Right, so what we talked about in this first tutorial is trying to be able to show that the excess risk of ERM can be small if we have certain properties of the function class. Right? And so how did we do this? We started by doing this decomposition that showed that the estimation error can be bounded by this quantity. We took this kind of naive upper bound that we're looking at the maximum possible value that could be achieved with a function class, and showed that this can be characterized in terms of the Rademacher complexity of this function class. And we talked about how this Rademacher complexity is much easier to actually bound because we have this Rademacher calculus that allows for using familiar transformations of functions that we would like to do. And we talked, and we were just talking about how if we have this L layer ReLU network where each layer's weights are bounded by B, then we can guarantee that the excess risk is small if the number of samples is something that's growing with B to the L. Right, and something we kind of glossed over and that I'll be talking about in the next tutorial today is this question of how we're talking about what is the excess risk of ERM, and that's a worthwhile statistical question to ask. But the next question is how can we actually guarantee that we can do something close to ERM in neural networks? Right? So this is something that's not obvious, and that I'll be talking a bit more about in the next tutorial. And just wanted to kind of foreshadow some of the talks that'll be happening in the tutorial tomorrow, and also some of the workshop talks, which is trying to kind of think about how strong, what's actually going on when we're talking about uniform convergence in relation to what we observe in neural networks. Right, so we've been focusing on trying to show that the gap between the population risk of ERM and the empirical risk of ERM vanishes as the number of samples goes to infinity. Right, and we mentioned this kind of intuition that the Rademacher complexity of a function class grows as the ability to fit random labels grows, right? Because this quantity gets larger if f of xi can be equal to epsilon I. And so this intuition that the greater the capacity of a function class to fit random labels, the more complex it is and the worse our upper bound is something to note, right? Because we can just consider this situation where we have a distribution P and some hypothesis class, where the best possible risk that can be achieved by any function in the hypothesis class is sigma squared, which is a positive quantity. Right, and we can consider f hat n that is an interpolate. Right, so it achieves, let's say, 0 empirical risk. Right, so because the population risk is bounded from below by a positive constant, we know that this interpolator must be fitting noisy points, right? If we have a lot of samples, and there are definitely some noisy examples, and that the Rademacher complexity of this function class is 1. Okay? Because whatever function class we're dealing in that can guarantee that it's going to be an interpolator must be so large that this is going to be equal to 1. Right? And so this bound in particular gives nothing, but even more than that, we can't really hope to have some type of uniform bound like this, right? We can't actually hope that this quantity is going to vanish as n goes to infinity. Right, the absolute best thing that we can hope for is that the risk achieved by ERM is something that vanishes and goes to sigma squared, or not doesn't vanish, but goes to sigma squared itself. Right, so this whole enterprise of uniform convergence seems a bit poorly suited for this type of situation. Right, and this is something that will be discussed a lot in the next few days. And I just wanted to show an experiment that really shows that such a thing does happen with neural networks trained by gradient descent. You can have a kind of Gaussian mixture model of data where you take some fraction of the training data and flip them randomly. Right, so in this plot, we have like 15% of the data has random labels. And if you train a neural network by gradient descent for this data, and you have like very few samples and very high dimensional data, then what you'll see is that the training accuracy converges to 100%, and the validation accuracy converges to the optimal 85%. Right, so this is a distribution where the best you can get is 85% because 15% of all the labels are random. Right, and this is something that not only just is true in the experiments, but we can actually prove that this really does happen. And this seems to conflict with a lot of these intuitions that we developed in the uniform convergence setting. And I think that will conclude what I've prepared for this tutorial.
Thanks, Spencer. And also giving us back on time. There's a few more questions I think we could take. Over the, sorry, question. I'm curious, like, do you think when you say that this, in this setting of benign overfitting, all of the questions, that those situations hold up, even not in the benign overfitting setting, or do you feel like that you're confident in another setting, but now in this setting?
Yeah, I mean, I think I'm confident in them in the other setting as far as theory goes, right? Like we know that it is the case that if you have samples that are more than 2b to the L, you will have population risk as close to the empirical risk. Right? We know this, but the question is like, what are the actual b's that we observe in neural networks, right? And if they're so large as to make these things useless, then yes, they're true, but they're not actually applicable to what we're doing. Right? So in that sense, if you're closer to this regime where the norms are large, or where you have basically all the complexity measures that we know are much larger than the number of samples, then it seems that there's something else going on that requires further investigation.
How big is the 2-layer neural net that you trained?
This holds for anything. So like this holds for width 1 also. So this holds for linear classifiers or 500 or 15,000. It's the same picture. Yeah.
So the gradient descent to the random.
Yes. Oh. Yeah, I think we can put them on the chat.
I know why you call this.
Yes. Okay. So we call it. I think also this will be talked. This whole topic will be talked about a lot tomorrow. But we call it. Well, first we call it overfitting because then there is some noise level and we're achieving zero empirical risk. Right? And we call it benign because it's behaving optimally. Okay, so this is the kind of surprising thing is that you can look at an estimator that's achieving zero risk on a problem where we know that there's some noise. So it is overfitting to the noise, but if it's still able to perform optimally or at least perform well, then it seems that this overfitting is like somewhat benign and not as harmful as we may have thought from classical statistical learning.
Could you comment briefly on some other settings besides uniform convergence that you think are interesting? Like in uniform convergence, we studied the soup. Are there other quantities that are kind of interesting to study besides the soup?
So I guess I feel like these are the main uniform convergence type tools, but there are other classical tools in statistical learning that you can use to show that the empirical is close to the populations, like compression-based bounds or stability-based bounds are also provide this guarantee that the empirical is close to the population, but doesn't really take this form.
Yeah, so I guess what I'm wondering is, so in the statistical learning setup, you, correct me if I'm wrong, but you're trying to say that all ERM, so all like empirical risk minimizers have this property that they are also, that the empirical risk is like close to the population risk. So you're not trying to distinguish between empirical risk minimizers, but maybe, again, correct me if I'm wrong, but I thought in practice, like a lot of the time you can have like a lot of minima, and then some of these are bad and don't generalize well, and then some of these do. So how do you apply the statistical learning framework, or if at all, in that kind of setting?
So these apply to any ERM, but this is also true that the type of ERM you have could affect other thing that's going on. This is something that will be talked a bit about tomorrow and in the next few days.
Okay, thanks, Spencer, and we'll continue in the second half of the Spencer tutorial in half an hour.